chapter 8.3, the inverse of a square matrix. We're going to verify that two matrices are inverses of each other. Use Gauss-Jordan elimination to find the inverses of matrices. Use a formula to find the inverses of matrices. And use inverse matrices to solve systems of linear equations. This section further develops the algebra of matrices. To begin, we're going to look at the real number equation, ax equals b. So when we solve for it, we have ax equals b, and then we multiply by a raised to the negative 1. And if we think about that, when we do solve for ax equals b, we think about dividing. And so just looking at this here, when we're doing this dividing here, remember that that is 1 over a, or a here, a to the negative 1. So therefore that cancels it out. And then so we get x equals this here. The number a to the negative 1 is called the multiplicative inverse of a because a inverse of 1 times a is 1. The multiplicative inverse of a matrix is defined in a similar way. So let A be an n by n matrix and let I(n) be the identity matrix. And there exists a matrix a to the negative 1 times a such that, we get this here, then a to the negative 1 is the inverse of a. So let's talk about an identity matrix first. An identity matrix has ones along the main diagonals and zeros for all the other entries. So for example, if we have a 2 by 2, it would be 1, 0, 0, 1. So the diagonals, these are the ones here, and then zeros for everything else. We can do a 3 by 3, which we'll do a little bit later. So it's 1, 0, 0, 0, 1, 0, and 0, 0, 1. So those are identity matrices, and we'll use them in a little bit. So we're going to find the inverse of a matrix. Show that B is the inverse of A. And so what we're going to do is we're going to say A times B, that should equal the identity, and then that's the same as B times A. So what we're going to do is we're going to multiply A times B. So we'll set it up, and then 1, negative 2, 1, negative 1. And so remembering when we do this, that it's by the row, by column. So when we multiply, this becomes negative 1 times 1 plus 2 times 1, and then we have negative 1 times negative 2 plus 2, sorry, not negative 2, plus 2 times negative 1. Then we'll do the second row, and so that is going to be negative 1 times 1 plus 1 times 1. Then we have negative 1 times negative 2 plus 1 times negative 1. And then, of course, double check, make sure I did it correctly. Negative 1, 2 is in my first row. Negative 1, 1 in the second row. And then these values here are from the column. So 1 and 1 and 1 and 1. And then negative 2 and negative 1. So that's good. So then we do the algebra involved in that. So this is negative 1 plus 2 is 1. This becomes a positive 2 and a negative 2, so that's 0. This is negative 1 plus 1 over here, so that is 0. And then this is 2 minus 1, which is 1. Okay, so AB, when I multiply A times B, I get 1, 0, 0, 1, the identity matrix. And so now let's do B times A. So that is, B is 1, negative 2, 1, negative 1. And then A is negative 1, 2, negative 1, 1. And then again, just to kind of help me out, we're going rows by columns here. Just got to help me keep it organized. So we'll do the first row. So this is 1 times negative 1 plus negative 2 times negative 1. And then I do 1 times 2, the second column, plus negative 2 times 1. Then I do the second row. 1 times negative 1 plus negative 1 times negative 1. Then we have 1 times 2 plus negative 1 times 1. And then, of course, double checking to make sure I put everything in the right spots. And then do the algebra involved in that. So this is negative 1 plus 2, so that's a 1. 2 minus 2 is 0, and then here, -1 plus 1 is 0, and then 2 minus 1 is 1. So therefore, we know there are inverses, therefore inverses, since A times B equals the identity, and also B times A is also the identity. So that's how you show that they are inverses of each other. Just good practice in doing that. So try letter B. Show that B is the inverse of A. Okay, if you tried this out, these are inverses, and so here's a work involved in that. Now you should be getting the identity matrix, which means you should get the 1, 0, 0, 1 for both. My only hint is be careful when you're adding and subtracting and when you're multiplying. So that's really easy to make tiny mistakes in there. Recall that it is not always true that A times B does not equal B times A, sorry, that should be B times A, even when both products are defined. However, if A and B are both square matrices and AB equals the identity, then it can be shown that BA also equals an identity. Okay, so in example 1, you only need to check that AB equals the identity matrix. Note that a non-square matrix cannot have an inverse. And then also note that not all square matrices have inverses. When a matrix does have an inverse, however, that inverse is unique.